In the linear time invariant digital system that is shown here, we want to prove that input samples x of n that are coming in and output samples y of n that are going out are related via this difference equation that is shown here. So this is what is referred to as the difference equation of system, and in the process of obtaining this difference equation, I am going to obtain and calculate or find the transfer function of this linear time invariant or LTI system as is described. Reason for it, it's LTI is because, as you can see, operation is just based on add and subtract and some delay that are realized with registers or by registers. The equation says current input sample coming out of the system equal to xn minus 1, or basically 2 sample delayed of input samples, minus 5.1 y of n minus 1 minus 0.75 y of n minus 2. Okay, the quickest way to do this is just, there are many ways, but one quick way is let's name this intermediate node as wn, which we can also write it this way, wn, n index means index of sample. Using z-domain analysis, I can say that wz, which is effectively z transform of wn, is equal to a delay, which is z minus 1, multiplied by whatever value we have here in z-domain. What is that value? As you can see, x of n, which means the z transform of that is x of z, is what we are subtracting from according to these polarities that are shown here. So we are taking wn and we are multiplying those samples by 5 and then subtract them from the input, as well as taking y of n and multiply the samples of y of n by 0.25 and then subtracting again from input. So I can say wz is the delayed version because of this register of x of z, which are the input sample, as I said, in z domain, minus because we have the minus here, so I'm going to say minus 5 times, as is shown here, 5 times the wn in z domain, which is wz, and then minus 0.25 times y of n, and minus because of this negative sign here, and so we're going to get minus 0.25 and yz. So that's one equation. Now let's just clean that up. I'm going to use it. If I clean that up, I can just reshuffle things around and it become this way. So keep wz on the left side, but I'm going to shift this multiplied by z minus 1 to the other side. It become plus 5z minus 1 wz equal to z minus 1 x of z, and negative 0.25 z minus 1 y of z. Okay, so let's keep this as for now. Now let's focus on, let me change the color so that it's easily observable. So let's now focus on this portion of the circuit, this portion. So what is happening in that portion of the circuit? We are seeing that samples of y of n are basically delayed version because of this register, which causes one sample delay of what is being produced or generated here, right behind the z minus 1. So I can say in z domain, y of z is the delayed version of, and right before z minus 1, what's happening? We have samples of wn, which in z domain are wz, minus 0.1 samples of y of n, so minus 0.1 yz. Alright, if I just reshuffle things around and clean up, what I get is this outcome. I get y of z divide by, and then I get, here's what I get. So I get 1 plus 0.1 z minus 1 y of z is equal to z minus 1 wz. So all I'm trying to say is I can just clean up. So I can just say, all right, maybe the best thing to do then is just keep this as equation 1. Now in equation 2, I'm going to multiply in here. I'm going to multiply both sides with z minus 1. So here we have z minus 2 and z minus 2 then, because I multiply both sides by addition of z minus 1. Now what's the benefit? This thing, I can just substitute it from equation 1. So what I can say from equation 1, I get 1 plus 5z minus 1, substituting z minus 1 wz, which is the right hand side of the equation 1 with its left hand side. So I get 1 plus 0.1 z minus 1 yz equal to z minus 2 x of z and minus 0.25 z minus 2 y of z. We are almost there. Let me change the color so that it's clear what I'm writing. So I am going to highlight the functions, basically input-output signals in Z domain, so that you can see what's going on. Okay, if you multiply and shuffle things around, obviously this portion is 1 plus 5.1 z minus 1, and then plus 0.5 z minus 2 if you multiply. And then we need to also move this from the right side of the equation to the left side, so everything that is related to yz is packed in one side. So if I do that, we end up with 1 plus 5.1 z minus 1, and then we have 0.5, and then this one goes and become a positive on the other side, adds to 0.5, so become 0.75 z minus 2 times yz equal to z minus 2 x of z. All right, we are almost there. So if you are interested in transfer function, of course, we can just use this. Let me put it this way. I'm going to use it here for further extraction, but if you want to play with this and obtain transfer function, here it is a transfer function. From this equation, if you just shuffle things around, you get yz over x of z, or basically z transform of output divided by z transform of input, which what we refer to it as transfer function h of z, equal to z minus 2, 1 plus 5.1 z minus 1 plus 0.75 z minus 2. So that is the transfer function. Okay, great. Transfer function of this LTI system. Now, if we want to find the difference equation, we need to effectively do inverse Z transform, which is easy in this circuit, and I'm going to do it. So the inverse Z transform basically becomes from what I wrote here, multiply 1 times yz becomes yz, which is yn. So, and instead of yn, I'm going to write it this way. So let me make sure you can see it. Okay, so yn, and then 5.1 z minus 1 times yz becomes 5.1 yn minus 1. Every time you multiply z minus 1 by a z-domain function, it's delayed by one sample. So it becomes plus 5.1. I'm going to move it to the other side. So negative 5.1 yn minus 1. 0.75 z minus 2 yz, for the same reason, becomes 0.75 yn minus 2 when you do this inverse z transform. Moving to the other side, we have to negate it, so it becomes negative 0.75 yn minus 2. And finally, on the other side, you have z minus 1x of z, which obviously means two sample delayed of signal x of n, so it would be x of n minus 2. And that is exactly what the target difference equation was stating, that yn is related to xn and previous samples of output via this difference equation. There are many ways to also to achieve these results. For example, we could have used the basic feedback loop and then start from there, but this is one quick way to achieve this. I hope that this is helpful.